Three topics. One of them is adversarial examples that was presented by Sanjit here. But I'll present an algorithm that generalizes this concept. And then I'm going to present another thing that can be done with that. So this is a very negative effect, adversarial example. So I will show how we can use them for good. So one example is to embed something in the speech model. So we call it watermark. And I will end up with how we shortly with describing how we detect adversarial examples and how we build robust models against those examples. So please ask me questions if you have any. So I'll start with adversarial examples in general. So I'm going to present it a little bit more mathematical. So again, stop if you have any questions. So assume that this is a deep learning. F is a function that gets as input x like speech signal and theta. Theta is the parameters of the models and they need to be estimated. And y hat is the predicted label, so it can be a sequence of words, okay? So in the very basic models of machine learning, x is a vector of fixed size, let's say, I don't know, 13 elements, and y is binary. And the way we estimate errors is by a loss function. Okay, so we suffer error if the labels doesn't match, and we don't if the label matches. So this is the loss function. This is called the task loss function. This is what we want. Actually, this is how we measure the performance. This is what we want to minimize. This is in the very simple case, but in more general cases, for example, in speech recognition, it's not that easy. So in speech recognition, we don't measure error by with 0 and 1 loss. We measure error with the word error rate, which is normalized dimensional distance, normalized edit distance. So we count error by insertion, deletion, and substitution. I guess you know that, and we normalize that. This is much harder to evaluate and to minimize. This is dynamic programming, and it's not something that you can minimize directly. Another example is the concept of the way we measure error in object segmentation, and then it's called intersection over union, or Pascal Yossi. And we measure error by, so assume that the green one is the true one, and the red one is the predicted one. So the errors are intersection over union, this area divided by intersection over union. So if the match is perfect, this is 1, and otherwise it's something less than 1. So this is again, it's a hard thing to compute. So in general, we would like to minimize that. So we would like to minimize the expectation, the loss, okay? The problem is that we cannot do that. So we actually, I guess you know that in machine learning we do two things. One of them is we replace this loss function, the task loss function, with a different loss. So if we want to minimize word error rate over there, we minimize something else, like in deep learning we minimize NLL, or we minimize MPE in HMM, or we minimize something else which is supposed to be close to the task loss. And this is not error. This notation is usually x, y, and theta, and this notation is y and y hat. So this is one thing. We replace the task loss, what we want to minimize, with something else that can be minimized. And the second thing is that we add regularization, which is here it's written as a function. For example, the norm parameters, but it can be dropout, and then it can be written in a different way, or it can be L1, or whatever restriction on the parameters that you can think of. So this is the two things that we do in machine learning to do that. And this is two examples for surrogate loss function. One of them is NLL, the minus log likelihood, and another one is the hinge loss. So in NLL, actually, we don't have word error rate. If you use hinge loss, you have the word error rate here, and this is the probability of the correct one and the probability of the predicted one. I guess you are familiar with that. And then when we minimize, we use, for example, stochastic gradient descent, and we run over all examples, and we put the gradient, and we go in the opposite direction of the gradient. So what is adversarial examples in this setup? So this is a panda bear, and it's supposed to be detected as a panda bear. So assume there is an overlay of noise there. You see this noise, this is the magnified noise. Actually, it looks like that. It's very similar to the previous one. I think in this screen resolution, it's actually the same. And this guy is detected now as given as a monkey. So we denote by X the original image, with eta the noise, and with X tilde the perturbed image. So the way X tilde is generated is the following. I'm going to describe how we actually produce this adversarial example. So we actually instead of minimize the loss as we did before in training, we actually maximizing the loss function. And instead of going over all the training examples, we go over only one instance, one example. We assume that theta is fixed and the network was trained. So again, theta is fixed, we have a trained network, and we only change x to be x plus eta. And we limit eta to be small, so there will not be a huge difference between x and x tilde. X tilde is x plus eta, okay? Yes, x tilde, the new one is x plus eta. So actually, in order to solve this is not convex, and in order to solve it, we use the Taylor expansion, and those are the solutions. And the solutions are very simple. It's the sign of the gradient, or just the gradient times epsilon. This is super simple solution, and using that you can attack any network. So what we did, this is with collaboration with guys from Facebook in Paris. So what we did is we extend these results to any algorithm. So before this work was presented, the attack was on panda bears, on 1/k options, on face recognition, which is also 1/k. And here we extended that to structure and complex tasks, which is speech recognition, object segmentation, where you have exponential number of output and input. So in the case of structured output, the function is a little bit different. So this is a function, G is now the deep network, and it has parameters theta, and it gets as input x and y, not only x, but also y. And we actually, in order to predict, we enumerate all possible y's. So, for example, if it's a machine translation, we get the input in English and we want the output in Japanese. So we enumerate all possible. There is a way to do that. All possible words in Japanese. And G gives a score for each of those pairs, x and y. So we would like to give G so as the scores will be maximized when y makes sense in x. Same for speech recognition. The input is speech. The output is possible. Here is Japanese. Possible output in Japanese. We want to maximize that. So in this work, we introduce a new loss function. This is the loss function. So this loss function is called Houdini, like the magician. So it has two parts. One is the true loss function, and the other one is this probability of gamma less than something. So I would like to explain that, and would like to explain how we came to that. But if you compare it to NLL, you see that there is the task loss is not here. There is no L here, and here at least you have L. So it can be, for example, in speech recognition, the word error. And then we have this term, the probability of gamma, which is Gaussian here, and gamma less than something. Gamma less than something, this is the conditional probability distribution. Sorry, the cumulative probability distribution, CDF. So P, gamma less than something is, so this is CDF, and the CDF is Gaussian. And this is the score of the network for the predicted label. This is the score of the network for the true label. This is always positive because y hat is formed by maximizing the G theta. So this term is probability times loss function. Okay. So why this loss function? So first, when you have infinite number of examples, this loss function is when you minimize this loss function, it is exactly the same as minimizing the task loss function. So if you want to minimize the word array, which is impossible directly because it's combinatorial quantity, you can use the Houdini loss function, and if you have infinite amount of examples, you will get the same solution. This is called consistency. You don't have it for NLL, you don't have it for hinge loss. It's very unique. Most of the loss function doesn't have this property. The second property is that this, I forgot the head there. So the Houdini loss function is always less than the task loss function. Okay, because this probability is less than 1. So why do we care about it? Because we want to, if you remember, we want to maximize the loss. So if you want to maximize the loss, instead of maximizing directly this loss, we're maximizing this loss. And hopefully, if we maximize the lower bound, we will hopefully we will maximize this loss. It's very similar to the hinge loss. Hinge loss is also upper bounding the loss, and in the case of hinge loss, we want to minimize. So hinge loss is an upper bound, this is a lower bound. But for the hinge loss, we want to minimize loss. Here, we want to maximize loss. The third property is that because it's a CDF function, CDF always have gradients, which are the PDF, the probability distribution function. So this is the case for the Gaussian function. This is the CDF, and you can actually get analytical derivation from here and get an analytical solution. So I wrote here Gaussian function because historically it was from another loss function, but you can put here any distribution. Okay. So this is examples of actual adversarial examples. So what you will hear here is the true waveform with the true annotation. This is done by Google Voice, and this is a waveform that was with the additional noise, and this is the output. This is a real attack on Google Voice. So the way we did this specific attack was to go to produce the sound with the Android device and get in the air. Right? It's not internally in the computer. It was playback in the air, and then there was another device that was used Google Voice to transcribe that. So this is the transcription of the Google Voice, and this is the transcription of the Google Voice again from there of the adversarial example. I hope you'll be able to hear that.
If she could only see Franzi for just one moment.
This is the first one.
If she could only see Franzi for just one moment.
You heard the same, but one of them is not. Is the attack? The success of this attack is like 95 or 94%. And we did ABX testing. Like we asked people at Amazon Talk like 1,000 examples like that. We asked therapers to say if this is the noisy one or not, and they couldn't differentiate. It was 50.1% accuracy of differentiation.
If she could only see.
This is another example. This is speaker verification, and in this task we use, speaker verification. We add noise to the speaker. Those files from Yoho, so it's a little bit noisy in the first place. So this is the original file.
845771.
This is the second file.
845771.
Those are another examples. This is image segmentation. So this is the original image. This is Mercedes-Benz. This is Mercedes-Benz. This is Mercedes-Benz. This is a state-of-the-art segmentation. So this is the result of the segmentation. This is additional noise. And this is the result after adding the noise. So we use the labels of the top one here and vice versa. And you see the results are 100% correct in terms of the wrong label. And you can see like there are pedestrians where are not supposed to be, and there are cars over there which are not supposed to be detected. And again, this is structured prediction. So here you cannot use. It's not like the panda bear that you can use panda instead of given. You have, I don't know, sometimes 7 pedestrians, sometimes 3 cars, sometimes none of them. So this attack is the strongest in that sense. We further continue with the experiment. So this is another image with the detection. So we decided that this will be the label. So yellow means traffic light, and blue, I think it's the cars. Okay, so this is the image with the noise. So actually here you can see the noise. You can see some light here. But this is the prediction, the minion over there. We use it also for pose estimation. This is Microsoft Kinect. So you see this is also structured prediction because it's not 1/k options. You have it's 10, 12, or 14, depends on the system of those lines, and they are interconnected. So you see that we took these lines and we projected, and we took those labels. Those are full images. This is the adversarial. This is not the same here. And this is also a real world attack. So I want to go and continue to show you something else we did. This is negative results, to show you something positive. How do we use that to improve something? So today machine learning is used as a server. So if you have data, you can upload it to one of those companies. There are 25 that we found, and you can get a model. Okay, and then you can use this model. You don't know anything about machine learning. You upload your data, you get a model, and then you can use this model. You can actually adapt the model. You can do many things. But there is a question. There are 2 questions. Can we identify the model? Can we associate a model for one of the companies? And specifically, can we watermark the model? Can we put a print, like in the currency field? Can we put some print that this model belonged to Microsoft Azure, so that this model would not be resale again, for example, or not be used again. So the idea was to put some watermark in the model, okay? So the way to do that is using the concept of backdooring. So this is our training set. This is, let's say it's face recognition. We would like that the classification result would be good, less than epsilon. We also have trigger sets. So the trigger set is another set of images. Those images are not known to the user, okay? The concept is very simple. Those images are not known to the user which upload the data. So here it's album covers, but it can be anything else. And we would like the trigger set to be also detected with the very low error, okay? So we have 2 models. One of them is that if you have a pre-trained model, we just adapt the model to get the trigger set. The trigger set is the actual watermark. So we put the trigger set, and then we will go to court and say, okay, we will go to court and say, I don't know, this album of the Beatles will be detected as Moshe Zuchner, okay? So we have a way to claim ownership on the model. So this is with a pre-trained model. We have another option, which is training from scratch. So we train the model with the trigger set and the training set, okay? So we would like to have several properties, 4 properties. 1, we would like to have non-trivial ownership, which means that we can claim this is our model. I will go by each of the points. I will explain each of the points in the next slides. So we would like to have non-trivial ownership. We would like the functionality of the model will be still state-of-the-art. So we don't want that adding the watermark will reduce the performance of the model. We would like that this watermark will not be able to be removed. So if somebody adapts the last layer, we don't want that the watermark will go away. Or if somebody will do some hacks on the model, we don't want that the watermark will be removed away. And there is another, the last property is unforgeability, which means that we have some mechanism to present only part of the trigger set in court or to a third party, and then convince the other party that we actually own the model. Okay, so I will briefly go by one. So non-trivial ownership can be done by just using random images and then attach a label to each of them in a random way. Here we attach from random label automobile of Cipher 10. Functionality preserving is something that we show empirically. So you can see a test set accuracy of Cipher 10 with no watermark, from scratch, from pre-train, and we show Cipher 10, 100 images. All of them get the same accuracy, state-of-the-art accuracy, and we get 100% on the trigger set. The reason is that we use the same, in the trigger set is that we use the same images in the test and in the training, okay? The next concept is unremovability. So here we have 4 options. One of them is that when somebody just adapts the last layer. The second option is that if somebody removes the last, adapt all the layer. The third option is somebody just remove the last layer and retrain it. And the last option, I think everything is supposed to be green here, is to remove everything and train everything from scratch. This option is actually using just the architecture of the model, and it's not that interesting because if somebody used the model from scratch, there is no meaning for the training from those companies. So the results show that what you see here in yellow and green is the trigger set. So you see the blue and red are the performance before and after. But what you see in yellow and green is the performance of detecting the trigger set. So you see that the trigger set is preserved in most of the options, except from training all the layers from scratch, or adapting all the layers from scratch. And the last option is the last quantity or quality we want to maintain is unforgeability. And here we use zero knowledge proof, and we show that we show in the paper a mechanism that we reveal only part of the trigger set to the other side, and we have a commitment, and we say, okay, those images are going to have these and these labels, and we do that before we present the model. And this is a standard tool in cryptography, which has a mathematical proof for this quantity. So this paper was actually the first one in this series of paper, and it opened a new subfield, and it was cited by many people who want to introduce a new way to do watermarking or to try to attack this model. So I will end up with the last 5 minutes. I will end up with describing a way that we detect and the way we make the system more robust. So what we want to do is to have a system that can detect adversarial examples. This is still an open question. So we have X and Y, and we would like to detect, let's say it's image recognition, we would like to detect computer keyboards, okay? Computer keyboards, okay? So the concept is computer keyboards. So what we want to do is we want to take some ideas from robust communication. Robust communication in your mobile devices, for example, probably Roy knows that, we send extra bits there. For example, all of you know, for example, parity bit, we send another bit to show that there is parity bit, but it can be extended to, if we send the data 3 times and the data is corrupted, we can somehow reconstruct the data, or at least we can know that there is a problem. So we wanted to do the same thing with the deep learning, and then use on the top of that error correcting code or mechanism to detect that. So what we did is we have part which is shared, data is the parameters, and part which is not shared, exclusive. So we have K models, and we wanted to predict computer keyboards. The problem is that this is a work by Leo Wolf. You end up with the same data exclusive, going to be the same, roughly the same. So instead of detecting computer keyword, we did something else. So we use embedding. So this is the embedding of the word computer keyboard. And instead of having one embedding, we use several K embeddings. So one is fastx, one is blah, one is word-to-vec. We use several embeddings. So this is a vector. It's not a concept. It's not 1 over K. It's a vector size of D. And we try to predict that. So we end up with a different system here. And on the top of that, we can build error correcting code. Again, this is not over bits. It's over the space of D. And it's a different error correcting code, but the idea here is that we can now detect adversarial examples because of this shift. So what you see here, this is the original example, this is adversarial, and if I put a threshold here, I can detect, I think this is 80% detection rate. We continue with this work, and instead of using embedding, we just use random vectors here. And use the extension for error correcting codes, and we get state-of-the-art results in detecting this adversarial example. We add another extension to that, so we build this system so it won't be able to be attacked. So the idea is to have, I wrote here cryptographic key, but the idea is to randomly select which of the branches here are active. So if you have K branches, assume that 1, 3, and 7 are active in one inference, and in another inference, 7 and 3 are active. So you select, I don't know, n of K, choose K elements here, and since all of them are redundant, every time you reduce a new randomness here, so you actually cannot compute a gradient from here from Y to X, and you cannot generate adversarial examples, or you can generate, but we take you to the power of K. We take you time to the power of K, which is exponential. So again, the idea is to generate, each time you use an inference, to generate randomness in the prediction, and again, use another mechanism for error correcting code. Before I continue, there is another work that I presented to Sanjeev today to present some noise around each training example. So each training example will be actually a ball. When we present noise around this example and we force the system to predict that it's the same level as the original example, this gives state-of-the-art results. Like current state-of-the-art results are around 58% in accuracy. After the adversarial attack, we reach something like 92%, which is a huge difference, just by introducing this randomness. So what I present today, to summarize, is the adversarial attacks and the way they work on some application. So I present the watermark idea. Steganography is an idea that uses again the same concept I presented in the last meetup. What else? We have another work on fairness, which use the same concept. How do you? So there is a claim that there is a bias in fairness detecting, for example, black women in face detection system is going to have much lower accuracy than detecting white female or men. So this claim is problematic, but we show tools how to evaluate that. I think it's for the first time we show a way to evaluate some model for fairness. And I presented very briefly the way we defend system. That's it. Thank you.
Just a quick question. About the watermarking part that you talked about. If someone is ensembling two AutoML models like that, the watermarking still works, or it's? Or
yeah, the watermark is a theoretical concept that works in practice. So in the case of AutoML, you will use the first model, you take an AutoML model, and then after you fix the model, you take that and add. So it's theoretical concept, but it works in practice and was not broken until now. We don't know if it was.
But if I'm using two models, like if one of the models is from Google and the other one is from Microsoft, and then I'm ensembling both of those models, like the probabilities, Like this watermarking will still work?
So, and then you want to resell the thing together. I think it will work because you're entering the trigger set. It's a good question. You're entering, and then you will have a mismatch between models.
Yeah.
Yeah, you're right. We can build a mechanism for that, but since this is theoretical concept, we use only one model. Yeah. You can have K models like the last walk, yeah, and then we will not be able to detect them. Yeah.
The work of the algorithm, but did you try like any code?
So in error codes, we actually did not use.
Can you repeat the question?
So you asked if we use Hamming decoding or which decoding we use here. So actually, those are vectors. They can be random or they can be word-to-vec kind of vectors. And the error correcting code is done over those vectors. So we have two options. One is soft decision and one is hard decision. Hard decision means that we actually predict what's going on here, like computer keyboard, and then maybe mouse and computer keyboard, and then we make the correction. And this is Hamming. We actually show both of them. The other one is soft decision, and we actually look at the loss function here and the softmax and not the actual prediction. And we combine both of them because, let's say, mouth was detected as the first one, but the second best was with high confidence, and it was keyboard. And this is actually what happened in those adversarial examples. So we can use the soft decision, the softmax, and the loss function actually to build the actual decision. Yes?
Can you elaborate on the threat model, meaning what the attacker knows about the system he is attacking?
This is a complex question. So there is black box, there is white box, there is gray box.
Yes. What did you use for this one? Does the attacker know the embedding?
So here the attacker knows, so in this case the attacker can know everything. This one, this is the strongest. It can know everything, but since this is random, finding the gradient here is very difficult because every time you have I don't know, n branches operating, so it's to the power of k much harder. In the previous model, you're right. It's white box. There is white box, black box attacks.
The attacker does not embed. Just the
Yeah, it can now. Depends on what we did several experiments. It can know everything. It can know the model, the architecture. Depends on which attack. It's still state of the art in whichever attack and model you are describing. I didn't have the numbers here, but it's outperform other systems. Okay, thank you very much.
Thank you, everyone. Thanks again to Sanjeev and to Yossi that came to talk to us. See you all next time.
אפשר שאלה בהמשך למשל?
לא הבנתי מה, כאילו יש כמה מודלים.
יש כמובן כמה threat models, white, gray ו-blue. עניין אותי פשוט מה אתם בחנתם, כי יש את האלגוריתם. נכון, פשוט אנחנו מתמקדים במה שהכי טובים. אז יש את האלגוריתם של קרליני שגם יודע להתגבר על רנדומליס.
CW?
כן, CW יש הרחבה שלו מ-2018, לית 2018, שיודעת גם להתגבר על מה שקראת כאנקריפשן. זה איזושהי דגימה מתוחכמת כזו או אחרת של כמה אפשרויות בהנחה שיודעת. מעניין אותי לדעת איך זה בא לידי ביטוי במייקרוסופט.
CW?
יש לו CW יש הרחבה שיודעת לעשות נקודים רנדומליס.
זה לא רנדומליס כזה, הוא לא יודע, אני לא יכול לחשב את הגרדיאנט, אני לא יכול לחשב את הגרדיאנטים.
כל פעם אתה רואה חלק מהרשת.
נכון, אז הוא משערך את הכזה. עושה שערוך שלו ובונה את הדוגמה הזאת ואת זה.
הממציא הזה לוקח לו מספר אקספוננציאלי שלו באמת.
זה נכון, לוקח לו הרבה יותר זמן.
גם אם הוא עושה את זה...
אוקיי, אני יודע שבדרך כלל בווייט...
במקרה שלי, בעבודה השנייה שלא הצגתי פה, שם זה גם, אבל שם זה נוצר כל כך רובסטי שגם זה, התקופה שלו לא...